All right, so this is where we left off last time. We learned how to predict the effect of a stress on an equilibrium, and we learned to predict what the shift would be in the equilibrium. Now we're going to learn to quantify that amount because remember, it's important that chemistry is a quantitative science, so we can make more precise and exacting predictions and make reactions go in the direction we want them to go. So if we look at these numbers here, these are what are called the equilibrium concentrations of reactants and products. So when this reaction reaches equilibrium, then um, this is the amount of reactant A, this is the amount of reactant B, this is the amount of product C, and this is the amount of product D that occur at this initial equilibrium. So what we're going to be talking about is something called equilibrium position and equilibrium constants, both of which allow us to quantify the direction of the equilibrium. So when we start a reaction, we have only reactants. We don't know what the original concentrations of reactants were, but at equilibrium, they went down to these concentrations. And when the reaction started, there were no products. So the molarity of the products would have been zero. But as the reaction went, their concentrations increased, and these concentrations decreased until they reached this equilibrium. So we can see that there is more of the products than there are of the reactants. So the reaction shifts towards the products. By how much? Well, there's about 3 or 4 times as much of the products as the reactants. So it favors the products somewhat. But what the equilibrium constants and position allow us to do is to quantify just how much. Okay. So equilibrium constants are a way for chemists to express an equilibrium position numerically. Does it favor the reactants or products? And does it favor it a little or a lot? And then there's a numerical value for that. Okay. So an equilibrium constant is basically a ratio of the product concentration over the reactant concentration. So what does the word constant mean? It means it stays the same. So when you shift an equilibrium, when you cause a stress on an equilibrium, the equilibrium will shift in order to minimize that stress and reestablish the equilibrium. So the amounts of reactants and products will change, but the ratio won't. So the product, the equilibrium constant, stays constant, it stays the same. So the only thing that can really change an equilibrium constant is temperature, because equilibrium temperature needs to be constant for the equilibrium constant to stay the same. Okay. So KEQ stands for equilibrium constant. It's equal to the concentration of, square brackets means the concentration of whatever inside the brackets. So the concentration of products over the concentration of reactants equals the equilibrium constant. Okay, so if we go to this generic equilibrium that we had a minute ago, same concentrations at equilibrium. So we would take the concentrations of the products over the concentration of the reactants. But what do we do to them? Do we add them up? Do we multiply them? Well, as it turns out, I'm getting ahead of myself. So this is a kind of a visualization that if there's more products than reactants, then the equilibrium constant value will be the numerators greater than the denominators. So the value of the equilibrium constant is going to be greater than 1. If it's a lot more product than reactant, then the value of K is going to go up. So the higher the K value, the more it favors the products. Consequently, also true, if the products are less than the reactants, then the equilibrium favors the reactants. The numerator is smaller than the denominator, so the K value is less than 1. If it really favors the reactants, then the K value will be much less than 1. which tells you that the reaction really favors the reactants. So let's look at how we set up an equilibrium expression for this generic equation, where little a times big A, this would be the number of moles of reactant A plus the number of moles of reactant B, reversible reaction, number of moles of reactant C plus the number of moles of reactant D. So what you do is you take the concentration of the products and you raise it to the power of the number or of the coefficient. So as it turns out, the number of moles of reactants has an exponential effect on the equilibrium expression. Okay, so you take the concentration of C, the molar concentration of C, raised to the power of the whatever the coefficient is, and the same with D. So these are the products, and these are the reactants. So you might be asked to write this for this reaction. So it might look something like, well, so C would be raised to the third power, D would be raised to the second power, A would be raised to the second power, and B would be raised to the third power. So if you're asked to write the equilibrium expression, then this is what you do. And you just plug in the values that are given in the reaction. If you're asked to solve for the equilibrium expression or find the constant for this equilibrium, then you actually plug in these values. So the concentration of C would be 0.45 to the third power. The concentration of D would be 0.39 raised to the second power. Then once you remember the order of operations, you have to take 0.45 and cube it, then 0.39 and square it, then you multiply those two together. Then you take 0.1 squared times 0.15 cubed. And again, order of operations, 0.1 squared, 0.15 cubed, and then you multiply them. So you get those two numbers, and then you divide them, and you get 411. Okay, which is pretty significant. If the value is greater than 100, then it tells you that it favors the products by quite a large amount. Okay. So the equilibrium position would be that it favors the products by a large amount, 411. Okay. So just a reminder that a square bracket means that it's the concentration of whatever's in the brackets, and the exponents are the coefficients in the balanced equation. Okay. Now what if I give you a graph? Well, at the beginning of the reaction, we have all reactants. So hydrogen and iodine are the reactants, and it looks like there's 1 molar concentration of, or one mole of each of these. Okay. And there's no product. And so we could tell the forward reaction would be H2 plus I2 goes to HI, and there would be 2 HIs. Okay. So write the balanced equation for this equilibrium. So that would be it. We know these are the reactants because that's what we're starting with. We know this is the product, and there's 2 H's, 2 I's, so we need 2 there. Okay. Then write the equilibrium expression for this equilibrium. Well, it'd be the concentration of the products over the concentration of the reactants. And since there's a 2 here, we need to square it. And then solve for or calculate the K value for this expression. So we would find the equilibrium concentrations, not the starting concentrations, but the equilibrium concentrations. So at equilibrium, that's where the lines flatten out. So the concentration of HI would be 1 mole, and then the concentration of these two would both be 0.5. Plug those in, 1 squared divided by 0.25. So the K value is 4. So does it favor reactants or products? It favors the products, but just by a little bit. What about this? Okay, so if I ask you to solve for the K value, solve for the equilibrium constant, first thing you'd have to do is write the constant. So what would that be? See if you could do it on your own. Pause the video if you have to. Okay, is that what you got? Then plug in the values. And if we just say that there's 1, 2, 3, so those are the moles. So SO3 would be about 2.8, and SO2 would be about 1.2, and O2 would be about 0.6, maybe 0.7. So 2.8 squared over 1.2 squared times 0.6, and the K expression is about 9, which tells you what? It favors the products by a reasonable amount. Not a huge amount, but by a little bit. Okay, good luck on the study guide.